Hello maths fans, I am Dr. Tom Crawford from the University of Oxford and I'm here with a special video for Maths Week London, a celebration of all things maths happening across the UK's capital city. Today we're looking at perimeter and area, but not just for any usual shape. What we're going to do is to calculate the perimeter and the area of what we call a fractal. Fractals are objects that have a repeating pattern, which means they look the same no matter how closely you zoom into them. The Mandelbrot set is one of the most famous and most beautiful fractals, but we're going to start with something much simpler that you can create yourself at home, and it's called the Koch Snowflake. We start with an equilateral triangle. That's a triangle where all of the sides and all of the angles are the same. So if we call the side length here is going to be 1, and then all of our three angles must be 60 degrees because the total angle, of course, must be 180 inside a triangle. Now, the perimeter is quite straightforward for this shape. So P is just equal to the distance around the edge, which is 1 plus 1 plus 1. So we can say that the perimeter P is just equal to 3. The area is a little bit trickier. We have a formula for the area of any triangle, which is a half times the base, which we'll call B, and times the height, H. And the issue is here we don't actually know the height, because when we say height, we mean the perpendicular distance to the top of our triangle, where this is a right angle at the base. So we know the base is 1, so we can substitute that one in. We know, of course, the number 1/2, so the only thing we're missing is this height, H. But fortunately, we have quite a lot of information in our diagram to allow us to calculate H. So the first method you might think to use would be to use Pythagoras' theorem. So Pythagoras' theorem, a squared plus b squared equals c squared, tells us that the length of this side squared plus the length of h squared must equal this diagonal length, the hypotenuse squared, which of course is just 1. So we have a half along the bottom, so a half squared plus h squared must equal 1 squared, which of course is just 1. So now we can rearrange and solve this to find h. So h squared will be 1 minus 1/4. So h squared is 3/4, just rearranging, and then we square root, and h must be equal to √3 divided by 2. So now we know the value of h, we substitute this into our formula up here, and we know that the area of our equilateral triangle is equal to 1/2 times 1 times √3/2, which is the square root of 3 divided by 4. So in summary, for our basic equilateral triangle of side length 1, the perimeter is equal to 3, and the area is equal to the square root of 3 divided by 4. Now this is where things get really interesting, because now we're going to take our equilateral triangle and we're going to repeat a series of steps over and over again to generate our fractal called the Koch Snowflake. We begin by dividing up all of the edges in our diagram in its current state into 3 equal parts. The next step is to remove the central piece along each of these edges. So we take away the middle 1/3 along the left-hand edge, the middle 1/3 along the right-hand edge, and the middle 1/3 along the bottom. The third and final step is to now add 2 new edges in place of the one that's been removed, each of these also being of length 1/3 on each of the gaps. So we fill each gap that was in the center that's been removed has been replaced by one of these wedge shapes. And it's very important that the length of each edge in this picture, of which there are now 12 in total, each of them has length 1/3. So after one iteration of these 3 steps, divide your line into 3, remove the middle segment and replace it by a wedge. After one iteration, we end up with this beautiful star shape. To get the next iteration of our fractal, we just have to repeat the same 3 steps. So remember, the first step was to divide up each line into 3 equal pieces. Our second step was to then remove the central piece from each segment. And then our third step was to draw a wedge, or draw 2 other lines in a pointed shape in each of these gaps. So there we have the second iteration in our infinite process to generate the Koch snowflake. So remember, to get the final shape, you have to repeat this same procedure, these same 3 steps, again and again forever and ever. So each of these lines would have to be divided up into 3 segments. You remove the middle one, you add your wedge. You do this again and again and again on all of these lines, and this will become increasingly complex at each stage and eventually lead to your infinitely complex fractal. The Koch snowflake is undoubtedly an incredibly beautiful pattern, which in itself is pretty amazing, seeing as it came from such a simple set of rules. But we want to go further. We want to know what happens to the perimeter and the area. We have the values here for our original equilateral triangle, but of course at each step we are adding these extra lines to the perimeter, and this increases the area of the shape. So what we're going to do next is to try and calculate the final value of the perimeter and the area of the full Koch snowflake as we repeat these steps forever. So let's start with the perimeter. The original equilateral triangle, remember, had perimeter equal to 3, and each of its sides had length 1. And the trick to understanding the perimeter is to think about what we are doing at each step. Because the steps themselves do not change, we just repeat them forever and ever. But if we can understand what happens at each individual step, at each iteration in the fractal generating process, then we can try and work out what would happen if we did that forever. So our starting point is going to be to consider the original straight line of length 1. Because our first step in this process was to divide that line into 3 equal pieces. The second step was then to remove the central piece. So we remove this, leaving our line to now have a total length with a gap of 2/3. And then we added in 2 other lines, each of length 1/3. Because we added in 2 lines to replace the 1 that we removed, and those 2 lines were each of the same length as the 1 that was removed. So at the beginning, this had length 1, and then after that very first application of our set of rules, it now has length 4 lots of 1/3, 4/3. And the reason we only need to think about one particular edge is we do the same process to every edge of our equilateral triangle. So originally we had 3 edges of length 1. Each edge has undergone this process from steps 1 to 3. So each edge has increased from a perimeter of 1 to be 4/3, and we still have 3 of them. So the new perimeter is just 3 lots of 4/3, which is equal to 4. So the perimeter at step 2 is going to be equal to 4. Now for the second iteration, we again follow the same 3 steps where we take each line in our diagram, divide it up into 3 pieces, remove the middle piece, and add the wedge. And again, we have this shape repeated 3 times around the original triangle. We had the star shape, if you remember. So like before, instead of considering the whole shape, we can just look at what happens to this one edge and then multiply by 3 to get the total new perimeter. So we divide each one up into 3 pieces, remove the middle, and add our little wedge. So these are no longer going to be 1/3, but it is important to remember that they started at 1/3. So they started at 1/3, we divided up into 3 pieces, so each one is now 1/9, and there are 4 of them, so this one has 4/9 in total, because we have Each little line is 1/9, and we've got 4 with that bump shape. Same here, so that's 4/9. Same up here, this one's 4/9, and this one's 4/9. So the grand total here is 4 lots of 4/9, which is 16/9 after step 2. So we have 16/9 on one edge after the second iteration of the process. And again, there are 3 sides to our shape. So the new total perimeter is 3 lots of 16/9, which turns into 16/3. So now we know the value of the perimeter for the first 2 iterations of our fractal generating process. It begins at 3, then it goes to 4, then it goes to 16 divided by 3. But of course, we want to know what happens if we were to repeat this process forever. So what we really need to know is what is happening between each step. How does the perimeter change from one iteration to the next one along in this sequence? So remember, our starting length was 1. It then went to a length of 4/3, and then this jagged thing had the length equal to 16/9. And what's happened at each stage is we've multiplied by 4/3. 1 times 4/3 gives you 4 divided by 3. And if you multiply again by 4/3, you get 16 divided by 9. So what's actually happening through our 3 steps of dividing into 3 pieces, removing the middle piece, adding in 2 more, we're taking the original line, which had 3 equally lengthed pieces, and replacing it by 4 equally lengthed pieces. So that's why we're going from 1, 3 out of 3, is going to 4 out of 3. And then all we do in the next step is take each of these individual segments and repeat the same process. So because we're doing the same thing, the fact that we know what happens in the very first instance, 1 goes to 4/3, in fact means the same thing will happen at every step beyond that. So what this means overall for our total perimeter is that at each step we take our old value and multiply by 4/3. So at step n equals 1, when we had the star shape, we would have total perimeter equal to 3, the old value for the equilateral triangle, multiplied by 4/3. And then at step 2, which is the one drawn here on the board, we multiply again by 4/3. So that would be 4/3 squared. If I went forwards and did the iteration 3, then I would get a more complicated shape. We multiply the old perimeter by 4/3, and we'd get 4/3 to the power 3 after 3 iterations. So hopefully you can now see that if I were to do this n times, the total perimeter will be equal to 3 times 4/3 to the power of n, where n is the total number of iterations of our 3 rules. If we now plot the graph of this function with perimeter p on the y-axis and number of iterations of our fractal generating process n on the x-axis, we've got 3, so it'll start at 3 when n is 0. And then as n increases, we get a larger and larger power of 4/3. And that will actually increase very quickly. So our perimeter will look something like this. And of course, to get our fractal, we have to do this an infinite number of times. That's what it means to say repeat the process forever and ever and ever. And this is why fractals look the same as we continue to zoom in towards them, closer and closer forever and ever. So the final value of the perimeter in this case, the perimeter of the Koch snowflake, is actually going to go to infinity. Now let's think about the area. So the original value for our equilateral triangle, which was our starting point, was the square root of 3 divided by 4. And at each step, you can hopefully see from my picture, we continue to add little pieces. So these are being added forever, but they get small very quickly. So the question is, will our area also go to infinity like the perimeter, or will something else happen? That is what we're going to try and figure out. The calculation for the area is a little bit more involved than the one for the perimeter. And to begin with, we actually have to think about how many triangles, how many wedges or new pieces are we adding at each step in our fractal generating process. So if we think back to our original triangle, we just have 3 straight lines, and then for each of these straight lines, they then, in the first iteration, are replaced by a wedge, something like this. So for each edge, what we are doing is adding one new triangle. And this is going to be key in our calculation for the area. So for each edge, so one edge gives one new triangle. And this is going to be the same if I were to repeat this to get our second iteration. I would take one of these edges and add in a little wedge. So again, in the next step, each edge or each line gives rise to one new triangle. So we now know that at each new step, say step n, we add the number of triangles equal to the number of edges in the previous step, step n minus 1. So let's put some numbers in this. Let's look at the first few examples. So at step n equals 1, we have originally 3 edges in our equilateral triangle. So the number of edges is 3. And for each of those edges, we replace them with the spike. So we add 3 new triangles. Then on our next step, n equals 2, the number of edges of our shape is equal to 1, 2, 3, 4, 8, 12. And what we do is add 12 new triangles. And we can continue to fill in this table, working out what happens at n equals 3, how many new triangles do we add, and the fact that it's equal to the number of edges at the previous step. But what we want to do is come up with a general formula that describes this pattern. Now, after a little bit of thought, perhaps trying out some more values, perhaps drawing more pictures and counting the new triangles and the number of edges, you will in fact find that at step n, what we do is we add the number of new triangles equal to the number of edges, and that is given by 3 times 4 to the power n minus 1. So this is the number of new triangles added at step n. Now, whenever you have a formula, you should always check that these values work for some of our earlier, easier cases. So when n is equal to 1, for example, we add 3 new triangles, and 3 times 4 to the power 0 is just 3, so that works. Then when n equals 2, we have 3 times 4 to the 2 minus 1, that's just 4. 3 times 4 is 12, we add 12 new triangles. And you can check this, and this will in fact work for any particular step. So at the nth step in our fractal generating process, we add 3 times 4 to the n minus 1 new triangles. Now you might be thinking, what does the number of triangles have to do with the area? And the trick here is to work out what the area of these new triangles we're adding is equal to. Because in each step, we're actually adding on area. So the area never gets smaller. It's the original triangle, and then we make it bigger, and then bigger again and bigger again. So the area is always being added to. And the amount of area we add at each step is given by the area of the new triangles that we add. So the next step is to work out what is the relationship between the area of the new triangles added to those that are already part of our shape. So again, we want to think back to our very first iteration and the simple case of the equilateral triangle. So we started with our equilateral triangle of side length 1. And then each of our edges gave rise to a new triangle, as we've just figured out. And these new triangles have side length equal to 1/3 of the original side length. So each of these are 1/3 if these are 1. So 1/3, 1/3, 1/3, 1/3, etc. So all of these are 1/3. So now the triangle itself, the ones that have been added, these ones, they have length 1/3, 1/3, 1/3. So if you reduce each length by 1/3, then your area is equal to a length times a length. So your area is reduced by a factor of 1/3 times 1/3. So again, the length has been reduced to be 1/3 of the original shape, so your area reduces by 1/3 squared, because all of the lengths are reduced by this scaling factor. So the area here is 1/9 of the area of the triangle at the previous step. And in fact, this will be true for all of these new triangles that we add at each step. They have exactly 1/9 of the area of the triangles from the step before. If we call the area of the triangles added at step n, let's call that AN, then the area of those triangles is just equal to 1/9 of the area of the triangles added at the step before, which is then equal to 1/9, so 1/9 squared, times the area at the step before. And this will carry on forever and get us all the way back to our starting area, A0 divided by 9 to the power n. So the area of the triangle added at step n, which is what we're interested in down here, is exactly equal to the original area, which of course we know over here, so I can label this now as A0, divided by 9 to the power n. So now we know the total number of triangles added at step n and the area of each of those triangles, so the total amount of area added at step n is just equal to the two numbers multiplied together. So the total area added must be equal to 3 times 4 to the n minus 1. So I'm going to write that as 3/4 times 4 to the n, multiplied by the original area A0, multiplied by 9 to the power n. So I can write that all together and get 4/9 to the power n. And this formula down the bottom is equal to the amount of area added at step n in our fractal generating process. So to get the value added at a particular step, you just substitute in that value of n, and that tells you how much area you're adding to what was already there. So now that we know the amount of new area added at each step, we just add all of these together for different powers of this 4/9 fraction, and that will in fact give us the total area. So at step n, our area, AN, is equal to the starting value, A0, plus the first term at step 1 is 3/4 times 4/9 times A0. Then at step 2, we add in another 3/4 times 4/9 squared times A0. Then at step 3, this is replaced by a cubed, and we carry on like this until we get to the amount added at step n, which has the power n. And we can write this as a formula. This is just mathematical notation. It means the same thing. Add all of these together when this number starts at 1 and goes up to n. But we write it as the sum from k equals 1, the starting value, up to n, the end value of the formula. So 3/4 times 4/9 to the power k times A0. So this formula here gives you the area of your Koch snowflake at step n in the fractal generating process. We can in fact simplify this formula a little bit because we have a common factor of A0, so we can take that out to the front. Then we've got 1 plus the 3/4 isn't involved in the sum over k, so we take that outside. And then we've got the sum from k equals 1 to n of 4/9 to the power k. So it's the same formula, just written a little neater. Now, if you've studied A-levels, or if you're going to go on and study A-levels, you will come across this. But this is in fact a geometric sum. It's something that we know how to calculate the answer to. There's a formula that tells you what the total of this is equal to. So if we use that formula, this will in fact be simplified even further. And it becomes A0 times 1 plus 3/4. Now for our geometric sum, the total of this is equal to the first term, so when k is 1, so that's going to be 4/9, multiplied by 1 minus the common ratio, which here is 4/9, to the power n, the last term, all divided by 1 minus 4/9. And simplifying the fractions gives us our final formula of A0 divided by 5 times 8 minus 3, 4/9 to the power n. Substituting in the value for A0, our initial area for the equilateral triangle, we get the final formula for the area of our Koch snowflake at step n in the fractal generation process. Exactly as we did with the perimeter, to investigate this formula further, we want to consider the graph of the function. So again, we plot the area on our y-axis and the number of iterations, n, on our x-axis. So we know the starting value is equal to A0, which is √3 divided by 4. Now, as n goes to infinity, we want to look at what happens to our formula up here. So the first term is just a constant multiplied by 8, so that will not change with the value of n, but the second term will. And importantly, what we're doing here is taking the number 4/9, which is less than 1, we're taking this number to a larger and larger power. And if we take this, in fact, to an infinite power, or a very, very large number, this will go to 0. So our function will begin to increase as we move through these first few steps, but then it goes flat. And as n tends to infinity, it will tend towards a constant value. And that value will be given by this first coefficient here. So the final answer, in fact, will be the square root of 3 times 2/5 will be our final area as n tends to infinity. So in summary, the Koch snowflake is not only incredibly beautiful, but it exhibits this really amazing mathematical behavior. It has an infinite perimeter. The distance around the edge goes on forever and ever. But the amount of area inside the shape is given by this constant and finite value. Thank you everyone for watching. If you've enjoyed this video, please do remember to subscribe, and I'll be back soon with some more maths fun. Take care.